The huge Gondwana landmass lay straight over the South Pole during the late Ordovician, and the broad, uniform North African and Arabian shelf was an ideal platform to accumulate thick ice masses.
The evidence available to us from the Sahara suggests that the ice sheets were very large and continuous at their maximum extent, very much like the modern East Antarctic ice sheet.
The Antarctic ice sheet covers almost 14 million square kilometers. In East Antarctica, the ice sheet rests mostly on land, while large parts beneath the West Antarctic ice sheet would be seabed if the ice sheet were not there. On average, the modern Antarctic ice cap is 2 kilometers thick, but in places the ice column measures 4.5 kilometers. The late Ordovician ice sheet in Gondwana may not have been very different. Large areas covered by ice and great thickness means also great ice volumes. And this is the powerful control button that make glacial deposits so heterogeneous and the system so complex. A small change in climate can cause large volumes of ice to rapidly melt and raise sea level significantly. Likewise, build-up of additional volumes of ice on the ice cap extracts the water from the world's oceans and lowers the sea level. Climate, the size of the ice sheet, sea level, sedimentary facies, and Ordovician reservoir quality are intrinsically coupled. It's worth taking a closer look at where the ice sheet was and how the late Ordovician glaciation worked. The center of the Gondwanan ice sheet lay just south of the Sahara, maybe in present-day Chad. From here, the ice flowed outward into all directions. Rocks underlying the central parts of the ice sheet were eroded and the debris transported towards the ice margins. Here, the strata was deposited. Glacial sediments from the late Ordovician are preserved across Gondwana and have been discovered so far in South America, South Africa, Saudi Arabia, Jordan, Libya, Algeria, and Morocco. Knowing where the edge of the ice sheet was at a particular time is important, because this is where sediment is freed from the ice sheet and where the most significant sedimentary facies changes occur. So where was the edge of the glacier in North Africa?
We can say that the ice sheets terminated in northwestern Morocco. Okay, where we have the chance of connecting the outcrops together in a depositional model. And they appear to have stopped there because there's a major break in bathymetry. So a big change from where you have sediments of perhaps 20 meters or so in thickness being accommodated on the shelf to a rapid increase of about 400 meters plus of sediments of differentiated turbidites. So in that particular case, if you decompact the thickness of the Ordovician turbidites in northern Morocco, you're talking about very deep water in that part of the world. For the more prospective parts of North Africa, that's to say in central and eastern Algeria and in western Libya, the story is more complicated because the evidence for where we might find the limit of the ice sheet is now in the subsurface in the northern part of the Khadamis Basin. The further north you go in North Africa, the greater chance you have of truncation, tectonic truncation by the so-called Hercynian unconformity. So it's an open question at the moment.
The outward movement of ice within an ice sheet is concentrated in so-called ice streams. Most of the ice leaving the ice sheet passes through these large flow systems, which can be hundreds of kilometers long. Some ice streams flow at speeds of over 1,000 meters per year. In between the ice streams are zones of significantly slower moving ice. The interstream areas that in modern Antarctica account for 90% of the ice volume. Here, flow velocities rarely exceed a few meters per year.